What is term in logic? In mathematical logic, a term denotes a mathematical object, while a formula denotes a mathematical fact. In particular, terms appear as the components of the formula. This is analogous to natural language, where a noun phrase refers to an object and a whole sentence refers to a fact. A first-order term is recursively constructed from the constant symbols, variables, and function symbols. An expression formed by applying a predicate symbol to a appropriate number of terms is called an atomic formula, which relates to true or false in equivalent logic. For example, we can see here that this is a term. It has the constant, variables, and functions. And here we can see that this term is a part of the formula, and the formula itself relates to true for each real number at value of x. Besides, in logic, terms play important roles in universal algebra and rarity systems. Formal definition. Given a set V of variable symbols, a set C of constant symbols, and a set Fn of n-ary function symbols, also called operator symbols. For each natural number n is greater or equal than 1, the set of unsorted first-order terms T is recursively defined to be the smallest set with the following properties. Every variable symbol is a term. Every constant symbol is a term. From every n terms, T1 to Tn, and every n-ary function symbol f, from n, a larger term f T1 to Tn can be built. So we just can embed all these constant and variables in our function arguments, and we will receive a new term. And using then intuitive pseudogrammatic notation, this is somehow written as that term T is the x or C or this function f with application of T1 to Tn. A term denotes a mathematical object from the domain of discourse. A constant C denotes a named objects from that domain, a variable x range of the objects in the domain, and n-ary function f maps n tuple of objects to other objects of this domain. For example, if n is a variable symbol and 1 is a constant symbol, and add is a binary function symbol, then we can say that add n and 1 also can be built by the first, second, and the third term. And this term is usually written as just n plus 1 using the infix notation. So we just replace this prefix notation into and replace the infix notation. We put this plus in the middle. And the more common operator symbol plus for convenience. The term has the structure and the representation. Originally, logicians defined terms to be a character string adherent to certain building rules. So we provide these building rules here. And however, since the concept of the tree became popular in computer science, it turned out to be more convenient to think of the term as a tree. For example, several distinct character strings like these and these. So this is actually some character strings that you build by rules, and they actually represent the same mathematical object. They denote the same term and correspond to the same tree. So actually this is the left tree in the above picture. So we have this picture, and this is we have two trees here, and interesting that they represent the same term, mathematical object, as a mathematical object. It's a mathematical structure. But here we can say that all these three terms are same as this tree. Okay, and separating the tree structure of a term from its graphical representation on a paper, it is also easy to account for parentheses being only representation, not structure, and invisible multiplication operators existing only in structure, not in a representation. Two terms are said to be structurally, literally, or synthetically equal if they correspond to the same tree. So we can compare trees, and if they're equal, we can say that the terms which represent these trees are equal. But of course, that doesn't mean that if they have two trees and they're not equal, this doesn't mean that they not represent the same mathematical object, as we can see here, for example. The two terms might be considered semantically equal, as they always evaluate to the same value in the rational arithmetic. While structural equality can be checked without any knowledge about the meaning of the symbols, semantic equality cannot. For example, if the function interpreted not as a rational but as truncating integer division, then if the substitute n equal to the left and right terms of these above trees, they evaluate to 3 and 2 respectively. Structural equal terms need to agree to their variable names. The set of variables of term t is denoted as by variables t. So if they take some term and they have the function to which we put this term, and it provides to us a set of all the variables which are presented in this term. And they can classify the terms by this, meaning that term doesn't contain any variables is called a ground term, so we just have constants there. And term that doesn't contain multiple occurrences of variables is called a linear term. For example, 2 plus 2 is a ground term, we only have constants here. And hence also a linear term is x multiple n plus 1 is a linear term, and n multiple n plus 1 is a non-linear terms. These properties are important in, for example, term rewriting. So it is linear because it is doesn't contain multiple where are no more than one variable, for example. Strange why they not swapped here, because here we have only one variable, and this must be linear term. And here we have multiple variables, x and 1. This is not a linear term. I don't know why they may be error. Or maybe I don't understand something. Please write this in the comments. So I'm talking about this paragraph. Also, there exist lambda terms which can be used to denote anonymous function to be supplied as arguments to these functions. And an anonymous function is just a function which hasn't name, as we can see. For example, we can define this lambda term, which actually defines the mathematical object which represent the square function, power 2 function. And the general sum operator can be considered as a ternary function symbol taken at lower bound value, upper bound value, and function to be summed up, for example, this lambda function.